Imagine we run one database across two Kubernetes clusters. Cluster A is healthy, cluster B is healthy. Every database pod is still alive. Then the network link between the clusters breaks. Now should cluster A accept writes? Should cluster B accept writes? If both say yes, we can create two conflicting versions of the truth. If both say no, our healthy database is suddenly unavailable. That is the real problem. Kubernetes can restart a failed container. It cannot decide which copy of our business data is allowed to become truth. So let us build this architecture properly and see why a second cluster can increase resilience and complexity at the same time. Inside one cluster, Kubernetes already does useful work for a database. A stateful set can give each pod a stable identity. It can reconnect a replacement pod to persistent storage. An operator can automate provisioning, backups, upgrades, and routine recovery. But notice the boundary. Those controllers observe one Kubernetes API server. They understand the desired state inside that cluster. If the complete control plane disappears or the whole region becomes isolated, another independent cluster does not automatically inherit the database. We now have two schedulers, two networks, two DNS domains, two sets of secrets, and two storage control planes. Kubernetes sees two systems. We want the database to behave like one system. That gap is where the hard work begins. The useful model is not one giant disk mounted into both clusters. Instead, each database member owns its own volume. The members copy operations through the database's replication protocol. The database, not Kubernetes, decides which member is primary, which members are replicas, and when a write is durable. The recent CNCF example uses one MongoDB replica set spanning multiple Kubernetes clusters. One site is authoritative and fully managed by its operator. The replica site joins that same replica set, but its operator runs in a passive mode. Why? Because two independent controllers must not both initialize or reconfigure the same logical database. We need one owner for database level decisions. This gives us our first rule. Separate Kubernetes placement from database membership. Pods and volumes belong to clusters, replication and elections belong to the database. Okay, now let us connect the clusters. Four boundaries appear immediately. First is identity. A normal Kubernetes service is discovered inside its own cluster. The multi-cluster services API can export and import services and give them names under service.cluster set.local. But MCS is an extension. We still need an implementation from our platform or networking layer. Second is reachability. Every database member may need a stable hostname and a secure route to every other member. Pod and service address ranges cannot silently overlap. Firewalls cannot drop heartbeats or replication traffic. Third is trust. The clusters do not magically share credentials. Database users, TLS certificates, and trust roots must agree. Their rotation process must agree too. Fourth is storage. A persistent volume is owned by a cluster and implemented by a storage provider. So cluster A and cluster B normally use separate volumes. The database protocol moves the data between them. Service discovery only answers, where is that member? It does not answer, which member is allowed to accept this write. For that we need Quorum. Suppose we place two voting members in cluster A and two in cluster B. That gives us 4 votes. During a network partition, each side can see only 2 votes. A strict majority of 4 is 3. Neither side has it, so neither side can safely elect a primary. For writes, this is why the CNCF design adds a 5th vote in a third failure domain. The layout becomes 2 plus 2 plus 1. Now a surviving side can combine its 2 votes with the third vote and reach 3. The other side remains below majority. At most, one side can continue as the writer. The small 5th member is not decorative. Its location decides which failures the database can survive. If it becomes isolated with the wrong side, the result changes. There is also a latency cost. With majority acknowledgement, a write is not done just because the primary stored it locally. The primary waits for enough members to acknowledge it. If the required acknowledgement crosses a slow regional link, that network delay enters the write path. So topology is really a policy. It says which failures keep writes available and which network round trips our latency budget must pay for. Now let us fail cluster A. The remaining members first detect that the primary is gone. Then eligible members hold an election. During that interval, there may be no primary, so writes pause. After cluster B and the third vote form a majority, a new primary can accept writes. But our work is not finished. Clients need database-aware connection strings, drivers need sensible timeouts and retry behavior. An uncertain write may have reached some members even when the client received a timeout. Important operations may also need idempotency, so a retry does not apply the same business action twice. And the database is now degraded in a 2+2+1 design. The surviving 3 votes are the minimum majority. One more voting failure can stop writes. Again, automatic failover therefore means automated role change. It does not mean zero interruption, full capacity, or normal fault tolerance. People often describe split brain as 2 databases accidentally becoming primary. Majority voting is designed to prevent that. Only the side with Quorum should continue. But we can recreate the same danger operationally. Suppose both Kubernetes operators believe they own initialization, or an engineer forces a disconnected replica to become a new database, or traffic routing sends writes to an old primary before the new topology is understood. Now the consensus protocol is no longer the only authority. The safer design has one explicit database owner, one membership configuration, one certificate authority path, and one tested failover procedure. The secondary cluster can manage its pods without independently rewriting the logical database. So, should you build this? Often no. If your recovery objective allows a restore, tested backups may be simpler. If a few minutes of manual cutover are acceptable, an asynchronous disaster recovery replica may be enough. If every write is latency sensitive, a remote K2R may violate the service level objective you were trying to protect. I would ask 5 questions first. Which exact failure must we survive? How much data can we lose? How long can writes pause? Which side owns the database during a partition? And have we tested that failure with real clients, DNS, certificates, retries, and storage recovery? If those answers are vague, adding another cluster can make the system harder to recover, not easier. A single cluster spread across failure zones, plus strong backups and a practiced restore is often the better first step. Here is the idea I want you to keep. Kubernetes can keep database processes running. The database protocol keeps one history authoritative. To span clusters, we must deliberately bridge identity, networking, trust, and storage. Then we must place Quorum so only one side can write after a partition. Finally, our clients must survive the election and the uncertain outcomes around it. Multi-cluster is valuable when the failure objective justifies all of that machinery. It is not a free high availability switch. If this helped you reason about database resilience, share it with someone designing on Kubernetes and subscribe for more engineering mechanisms explained visually.